Hello everyone, I'm pleased to show our latest work on compact sense reconstruction and rendering, which we called MPGS. Our work builds up on the promotion of 3D Gaussian splitting, where 3D GIS has attracted significant attention in the industry for its ability to generate high-quality rendering. It still faces challenge when dealing with heterogeneous scenes, particularly in areas with weak textures. These areas are often affected by floaters, and the reconstructed geometry tend to be non-compact, that reducing the rendering quality. The latest work attempts to improve the geometric reconstruction quality of scenes by optimizing Gaussian property distribution. However, it still falls short in weakly textured areas of heterogeneous scenes, where a large number of floaters severely affect the geometry quality. We identify two key factors behind the failures in heterogeneous sense. One is the limitation of core map initialization, and the other is the optimization strategy inability to handle spatial floaters effectively. These factors interact in heterogeneous sense, significantly degrading reconstruction quality. To address this, we proposed MPGS, which aims to reconstruct heterogeneous scenes with actual Gaussian distribution, avoiding the influence of floaters and achieving efficient and high-fidelity sense rendering. The proposed MPGS, which consists of three core continuums: multi-plane initialization, multi-plane density control, and multi-scale geometric correction. These continuums can effectively optimize the distribution of Gaussians. Based on core map, the multi-plane initialization method introduced estimated monocle depths to segment the scenes into multiple planes, and performing uniform rezamping and densification within this plane. It can effectively improve the lack of initialization point in weakly textured regions, ensure a more balanced initial Gaussian distribution, and provide reliable reference point for subsequent optimization. Unlike the original density control strategy, we also proposed multi-plane density control. In previous work, global statistic pruning defined local Gaussian as a normal distribution and measured whether Gaussian was an outlier by calculating the distance from position to the local center. This is not applicable to floaters that are close to the surface of the object, and there may be misjudgment. By using the depth of Gaussian distribution, we adaptively lower the sense by conducting local statistics on each plane. The proposed method can more accurately identify floaters without being affected by different planar Gaussian distributions, and remove the floaters to reconstructed more accurately sense geometry. Considering geometry distortion and rendering error, we use monocle depth and rendered images to distinguish distortion and errors. Then use the scale decoupling of edge Gaussians to refine the distribution of edge Gaussians in the field areas. More importantly, Multi-scar structure similarity measure L adapt to evaluate the statically on real jumping point. It is worth noting that while this strategy may struggle in small regions, we have introduced normal depth regularization to provide robust supervision and mitigate this limitation. We conducted comparative experiments with baseline method on public datasets. In quantitative comparison, our method has achieved better performance in rendering quality and rendering speed. The training cost of our method is significantly lower than DRGS and GOF, and slightly higher than 3DGS, GS Pro, and SufferGS. We also analyze storage overhead, and our method achieve more complex sense reconstruction, utilizing fewer Gaussian parameters to achieve more efficient and high-quality rendering. Compared to other methods, the proposed MPGS alleviates the influence of floaters in heterogeneous sense, reconstruct the geometric fit the sense to the surface of object, and achieves compact sense reconstruction. We also visualized the distribution of Gaussian parameter. Obviously, 3DGS is disordered and several degrade the Gaussian distribution, especially for accurate and weakly textured air. On the contrary, MPGS reconstructed compact sense, and the Gaussian parameters fit the surface of the sense. In the visual quality compression, 3DGS and 2DGS are limited by floaters, resulting artificial and brownness in rendering. DNGS and GRGS are prone to failure in object edge reconstruction. The rendering result of GOF and SufferGS has ghosting. Our method achieves a clear appearance in modeling with fewer synthetic view artifacts and rich textural detail. More importantly, the sense geometry reconstructed by our method is faithful and reliable, achieve efficient and high-quality rendering. These are visual comparison of different rendering methods. However, MPGS also has some limitation. It is not applicable to nullambration and several occluded regions. Overall, our post MPGS can compactly reconstruct heterogeneous sense and achieve high-quality rendering. Thanks for listening.